lecture. We started the type binding, and I will just summarize the main formula we got last time. So we had an equation which was sum of the atoms and the orbital of the matrix element mu prime I prime mu I, the coefficient of the wave function a mu I of k, so equal epsilon k sum over mu I, the overlap matrix k with the element mu prime I prime mu I a mu I of k. So the A were the coefficient on the type binding basis for the atom orbital mu, atom mu orbital I. So this was the equation to solve, and the matrix element of H mu prime I prime mu I were given by the atomic energies for the atom mu prime and the orbital I prime. The type binding overlap matrix element mu prime I prime of kr phi So these are the matrix elements for H. I will signal the hopping term mu prime I prime mu I k. This is the H, and we had for this hopping terms T mu prime I prime mu I k is equal to the sum over the lattice vectors exponential I k r and the matrix element between the atomic orbitals. So for the atom mu orbital I prime centered on the atom mu prime here, the unit cell at the origin, and then the crystal field V prime of R, and the atomic orbital on the atom mu orbital. So these are the atomic orbitals. So this one is centered on the atom mu in the unit cell R. So this is what we had, okay? So this is for the hopping term, and then for the overlap matrix is just A is the overlap matrix between the type binding basis function. So between phi k r, so label for the atom mu prime and the orbital I prime. So that the type binding function constructed from this atomic orbital for the atomic mu prime, for the atom mu prime, then phi mu I of k. So these are the overlap terms, okay? So this is what we had last time for the type binding approach the general results for using the form that I gave you for the basis tight binding basis functions. So now we will start making some approximations to simplify, and the first approximation is that we considered very localized atomic orbitals, and therefore we will neglect some terms that appear in the overlap when one develops the overlap matrix elements. So the first approximation is that, considering that we have very localized atomic orbitals, we will consider that most of these matrix elements, mu prime, I prime, between the atomic orbital centered on different sites are zero. Basically, we will consider that all those that are not centered on the same site can be considered to be zero, vanishing. So we will consider that this matrix element phi of mu prime I prime centered on the atom, the mu prime in the unit cell at the origin, and the atomic orbital mu I centered on the atom mu in the cell R will be 0 for mu for R different from 0, and for mu different from mu prime. So if the atomic functions are not centered in the same cell and on the same atom, we will consider that this matrix element is 0, because the atomic orbital, we consider that they are very localized on the atomic site. Okay? So this is the approximation we will make for the overlap. And this implies that our A matrix element, or A matrix element here, mu prime I prime mu I, which is equal to sum over the lattice vectors exponential I k R, the matrix element between the atomic orbitals, minus E mu prime. Phi mu I of R minus d mu minus R. So this is what we had for the overlap matrix. We could simplify it, considering that, for all cases where one has a periodic operator, one can just reduce it to the sum over one sum over the lattice vectors. Okay? This is what we had seen. And this sum, using our approximation, simplifies. So considering this approximation, we are left just with r equal to 0, so we are left with v mu prime I prime of r minus v mu prime times v mu I of r minus v mu. Okay, and since we also want the orbital to be centered on the same side, not to be when they, or then not to be 0, for the matrix element not to be 0, we have to have mu prime equal to mu. And in addition, when mu prime is equal to mu, since the atomic orbital on the same atom are orthogonal in the atoms, then we have just delta mu prime I prime mu I. The only case when it's not 0 is when it's on the same atom, centered on the same atom, and the atomic orbital is the same. Okay? So the matrix element is basically the identity matrix. The one matrix. So also for the Hamiltonian we had one term that was just the overlap matrix and the atomic orbital. So also the H simplifies. So H of mu prime I prime mu I is equal to the atomic energy mu prime I prime times the delta mu prime I prime mu I. This was originally the overlap matrix, but it simplifies with our approximation, and then we have the hoping mu prime I prime term mu I of k. So this simplifies quite a bit our original equation, matrix eigenvalue eigenvector equation. Okay, so far? Now let's take the example of one atom per cell, and we consider for that atom the atomic orbital 1s, 2s, 2p x, 2p y, and 2p z. So one atom per cell, and we consider in the basis the atomic orbitals 1s, 2s, and 2p x, 2p y, and 2p z. Okay, now let's look at the matrix we will have, what one should solve with our approximations. So I will have a 5 by 5 matrix, since I choose to consider 5 basis functions. And for the H matrix, I will have in the diagonal. So I ordered my basis function in this order, 1s, 2s, 2p, x, and so on. So the first diagonal element will be the atomic energy of the 1s state, plus the T 1s, which depends on k. Then off diagonal between the 1s and the 2, well, I can write also for the 2s, the diagonal element, because it's just similar. So it's T2s, 2s. Okay. So this is for the diagonal part, and of diagonal, I will have just the T1s, 2s of k, and then I will have the complex conjugate of that element. Okay. Okay. One looks at the form of the T. It's just the complex conjugate. And then, okay, the other terms are similar, and one goes to the T1s 2pz. Okay. This is the last element of my row, and similar here, T1s 2pz star of k, and then the last element is epsilon 2p atomic plus T 2pz. Okay, so this is the matrix, and the vector is the vector of the coefficient A1s and so on up to A2pz. The coefficient of the function of the basis, the development of the eigenstate, Bloch state, in terms of the Bloch basis function, atomic basis function. So here one has epsilon of k, and then one has A1s and so on, A2pz. So this is the equation, the matrix eigenvalue, eigenvector equation that one would have to solve for 1 atom per cell and 2 atomic orbitals, 5 atomic orbitals, the one I listed here. So this means one has a 5 by 5 matrix to diagonalize okay, so that is how one solves the problems and the problem, and then from the diagonalization of that matrix, from the diagonalization one will obtain as solutions the epsilon k, the eigenvalue, so one will obtain 5 eigenvalues in this case, epsilon for each k point, and from the eigenvector one will get the C, the Bloch eigenstate, crystal eigenstate, so C k of J, which in R, so this is just 1 over n, the number of unit cells, sum over the lattice vectors, exponential I, K, R, and then one sums over the coefficients and the solution of the eigenvector solution, so AI for the eigenvalue J, phi atomic I of R minus capital R, and this is for J equal 1 to 5, since I choose 5 basis functions, binding basis function. So from the diagonalization, one obtains the spectrum, the energy spectrum, the 5 lowest bands, and the corresponding Bloch states that are written as linear combination of atomic orbital. And the unknown coefficient will be A, which one obtains from the eigenvector. So one has the full solution this way. Okay? All right, so this is how in general one would proceed. How big would be the matrix if one had 2 atoms per unit cell? Yeah. Okay, so let's now consider some limits. So when one considers that the lattice parameter tends to becomes huge, one reobtains the atomic energies. So when the atoms are far apart, so I consider that A becomes huge. Then one obtains that the hopping terms, the T I prime I, here I'm considering the case of one atom per unit cell. But if one expands everything, one would obtain the same results also for more atoms per unit cell. So when the atoms are far apart, the Tij tend to 0. One has that the product phi complex conjugate of the atomic orbital I prime times the crystal potential times the orbital I tends to 0. When the atomic state are centered on different atoms and the distance becomes very large, the product becomes 0 because the atomic orbitals have an exponential decay. So the overlap tends quickly to 0. And also in the case where the I is equal to I prime, it's the crystal field that goes away and this also goes to 0 in the tight binding approach. So when the atoms are far apart, when A tends to infinity, when it becomes very large, one recovers the atomic energy. Recovers so one recovers the epsilon I atomic. So these go become flat as a function of K, and the value is just the atomic energy, and the states that are the solution are these states with the coefficient becoming 1. So the eigenstate or the solutions are block functions. That is phi k of R is equal to 1 over n, the sum over the lattice vector exponential in ik R phi I of R minus capital R. So the eigenvalue are the atomic energy, but the eigenvectors are written as linear combination of the atomic orbitals because they need to be block states, and they are in this form which satisfies Bloch's theorem. So the solution are involving all the atomic size. Okay? It needs to be an extended state because we are looking at a crystal, and in a crystal the solution, the electronic solution, must have the form, the block form. Okay? All right, so this is for the limit when the atom are getting far apart, the atomic energies. So now let's look at the case of an isolated band. It is a band that is far away in energy from the other bands. So let's consider another limit, the limit of isolated band. For instance, the 1s band. In the atom, the 1s state is much lower than all the other states, well separated, and let's say in the crystal it remains rather similar. So in the case of one atom per cell, and if I consider that my atomic energy epsilon I is much smaller than the other atomic energies, and okay, this would be the case of the 1s band. To be more general, let's say that the energy I consider is really well separated from all those above, and also from all those below. If I consider the one state, there is nothing below, but more generally, I can consider just this limit. And I consider that the Hoping terms, Tij, are much smaller in absolute value than any of these energy differences. So epsilon I plus or minus 1 minus epsilon I is much larger than the magnitude of my Tij. Then in this limit, the diagonal element of the matrix go to 0 of my Hamiltonian matrix. Diagonal element of the matrix. So the off-diagonal element go to 0, so I just remain with my diagonal element, and the diagonal element is epsilon I of k is equal to the atomic energy plus, this is the term with R, capital R equal to 0, so phi I of R, the crystal field, times phi I of R, plus the sum over the lattice vector different from 0 of some. So the sum over the vector different from 0 here, exponential I k capital R. The atomic orbital of R crystal field times the atomic orbital centered in another unit cell. Okay. So this is what we get when we are in the limit of single band, that is a band that is well separated in energy from all other bands. In that case, the off-diagonal go to 0, and one remains with the diagonal, and here I forgot. Okay. This is the diagonal term that gives us the energy. Okay, and this okay, so if one looks at these terms, so one has the atomic energy, which doesn't depend on K. One has also this term, which doesn't depend on K. And this is just a shift in energy. And it is the energy shift due to the crystal field. So it's just the expectation value for the atomic state induced by the perturbation, the crystal field. So this is just the energy shift This is just the energy shift due to the crystal field. So the atomic energy is just a shift that corresponds to this perturbation, first order perturbation in terms of the crystal field. But it doesn't depend on K, so it's the same for all K in the brilliance ring. And then one has this last term here, which depends on K, which is going to give the dispersion to the band, and the magnitude measures actually the interaction with the neighbors through the crystal field. So this term is what will give the band dispersion. So K band dispersion and this is due the magnitude of the dispersion of the width of the band is due to the interaction with the neighbors. It's the interaction between let's say for the S state on one atom and the S state on the neighboring of the atom in the neighboring cells that interact because of the crystal field. Okay? So this is what is obtained in the tight binding approach in the limit of band, isolated band, like an S band. Okay, up to here? So in what follows, we will make some additional approximation, and in this sum, we will consider for the R only the first nearest neighbors. We will neglect the matrix element that involves neighbor that will be beyond the first nearest neighbors. Okay? Because the matrix element will become very, very small because of the overlap. The overlap between this matrix will become between the atomic orbital far away will become negligible. So in what follows, so for the coping terms, mu prime, I prime, mu I, in the sum that I have here, we will neglect interaction beyond the first nearest neighbor. And this is again a consequence from our assumption that we have very localized atomic orbitals. So for the overlap matrix, we consider only the on-site, that is the matrix element of the overlap for atomic orbitals that are centered on the same site. And for the potential, the crystal field, we go up to the first nearest neighbor because there is a field that makes, that binds or is in between the two orbitals and increases the product of the overlap. So for when, in the matrix element with the crystal field, we go up to the first nearest neighbor, okay? And for the overlap, just to the, we neglect even the first nearest neighbor, the overlap matrix. All right, so these are the approximations that we will make in practice to do calculations with the tight binding method. So now let's see what we get in the case of an isolated band. So the first example will be one-dimensional. And one-dimensional, so we consider a chain of atoms. And I will consider one s orbital. And so we are in the case of the isolated band. For instance, the case of the 1s band that is much smaller, 1s energy that is much smaller than the other atomic band. So in this case, if I draw the wave function, so I'm going along the chain with the atoms in the x direction. I have my reference site, the unit around the unit cell around the origin, with so this is my atom at the origin, and I have an atom which is centered at the distance a, and an atom which is centered at the distance, at minus a here. And since I'm talking about S state, I have an S atomic state centered on the atom at the origin. So this is my S wave function that is centered on this atom at the origin, and then I have an S wave function that would be centered on the atom at the position A. So this is the S wave function that would be centered on R1 that corresponds to A times the vector, the unit vector x. And I have another wave function here that is centered on the atom at the position minus R1. So in my matrix element here, I would consider the S wave function centered at the origin, and the S wave function of the first two neighbors, which are at the position A and minus A. And I need to calculate this matrix element. I will need to calculate this element. So the crystal field here, if I draw it, and I consider some potentials that are, let's say, atomic, like the crystal potential would be a sum of atomic potential, and the crystal field would be the sum of the atomic potential without the one at the origin. So I can imagine a potential that is attractive, Coulomb type centered on this site. Nothing for the potential here because it's removed in the crystal field, and another atomic potential that is coming from this atom here. So in this region where the atomic orbitals are overlapping, I have essentially this type of potential, which I can assume to be negative with the idea that the crystal potential is a sum of atomic type of potentials. So what I know is that the product of these wave functions times the crystal potential, if I integrate, I can expect a negative value because the potential is attractive here. So what I plotted here is the crystal field. Here the wave functions that are involved, and here the crystal field that is always centered in the reference unit cell at the origin. So now my matrix element diagonal term for the S tight binding state will be, it's a one-dimensional chain, so I have just kx. It's going to be given by the atomic energy minus the shift due to the crystal field, the constant shift, which I will call delta V0, and I know that this will be negative because it is just the matrix element of the wave function at the origin times the crystal field times the wave function again at the origin. So this is my correction. I know that the crystal field is attractive, so it's a negative potential, and this matrix element will be negative overall. So I just take the absolute value and I identify the delta V0 as the absolute value of this, and I put a negative sign because I know this is going to be the potential, the crystal field potential is attractive. So this is for my constant term, the shift. And then for the other part, the sum over R, I will have to sum over the first nearest neighbor at A and minus A. So if I consider the case A, I will have the matrix element between this orbital, complex conjugate, this orbital, and this potential, which is attractive. So again, I will have something, if I integrate overall, negative, and I will call it T T. And I put the minus because I know it's going to be negative. And this T is just the absolute value of the phi S centered at the origin. The crystal field and the phi S that is centered on the atom A. Okay, so I call this matrix element its absolute value T, and I know it's negative, so I put a minus T here. But of course, if I evaluate this times the crystal potential and I integrate, I will obtain exactly the same than if I evaluate this times the crystal field. It's the wave function here and here are the same. They are symmetric with respect, let's say, to this mirror plane. And therefore, this matrix element is the same if I have here minus R1 or plus R1, and this is just equal to my value minus T. So this is for the matrix element, and when I have this exponential to evaluate is just ikx times A plus I for this, so for this one, and for this other one it's going to be the opposite phase. So I will obtain a cosine, 2 times cosine. So 2 times the cosine of kx times A. Okay? And this is just clear for everybody? Ask question if it's not clear. All right? Okay, so this is the result in one dimension for the case of an isolated band in the tight binding approach. So now let's plot this. So I want this energy, epsilon, as a function of kx. Any question? Something not clear? No? Something wrong? Excuse me? It's okay. Okay. Now I'm concentrating in the Brillouin zone, so the region between pi over A and minus pi over A for my one-dimensional chain. So the atomic energy of the 1s state, let's say it's here. So it's epsilon atomic, the level is positioned here below the zero. It's a bound state. I will have this shift which will decrease the value. So this is my delta V0. So this will give me an average value here. And then these are just these two terms. The third term gives me the dispersion. So this will depend on kx, and it's a minus cosine. So I know it will have a form of the type, let's say, the interactions with the neighbors is large. I will have a cosine of a wave function here, minus cosine, and the width of this band, so the cosine will, the average value will be this one, the one of my first two terms, because cosine goes from minus 1 to plus 1, so the average value is 0. It's this value here. And the width here, the cosine, so the width is 1. I have a 2 here, which will give me, sorry, the width is 2 because it goes from minus 1 to plus 1, the cosine. So 2 times 2 times t, I will have an overall width here of my band that will be 4 times t. Okay? So this width of the band is measuring the interaction between the first nearest neighbors, that is this t, is the interaction between the first nearest neighbors. So the bandwidth is measures the interaction with the nearest neighbors. So this is how a tight binding band looks in one dimension for the case of a chain of atoms in the limit of the isolated band. Okay? Alright, so now let's go into dimensions. So 2D. And I will also consider the case of one s orbital and I will consider the case of a square lattice. Okay, so let's draw things. X, Y, and the square lattice. So I have atoms which are arranged like this. So I'm considering the case of s orbitals. So I have my reference atom at the origin with an s wave function, so spherical type of wave functions. And then my nearest neighbors are the atom 1 here, that is linked to the atom at the origin by the vector R1, the atom at the position minus R1 here, the atom here at the position R2, and the atom here at the position minus R2. So these are my nearest neighbors, my 4 nearest neighbors that I will consider in the sum of lattice terms in the diagonal part of the time-binding H matrix. So now the energies I will get in this case, so I have the energy of my S-band that will depend on K, Kx and Ky. In this case, it's 2-dimensional. So again, the diagonal term, the first R is the atomic energy of the S state. Then I will have the shift due to the crystal potential, the first order perturbation term on the atomic state S at the origin. So this is phi S of R, the crystal field, phi S of R. This is the atom centered at the origin, the atom centered at the origin. And this again, since the crystal field due to the nearest neighbor felt by the S orbital at the origin will be negative, attractive, I can put a minus and a delta V0, where delta V0 is positive, the absolute value of the matrix element I'm considering here. So this is for the constant shift. And then I have to sum over the contribution of the nearest neighbors, R1 minus R1, R2, and minus R2. So I will get 4 terms with, as a phase for R1, it will be just exponential I kx times A. So I have a square lattice with A lattice parameters, so the separation here is A, and I'm getting exponential kx A for the I k times R1. Then I have the matrix element phi S for the orbital at the origin, V prime, the crystal field, times the orbital at the position R1, the nearest neighbor at the position R1. So this is the contribution for this neighbor R1. Then for the minus R1, I have here exponential minus I kx A, okay, times the metric element phi S of R, V prime of R, phi S of R plus R1. Then I have for R2, it's going to be exponential I k y times A. And then the matrix element is this one times phi S of R minus R2. Plus, and for minus R2, I'm obtaining also a minus in the phase here, exponential minus a I ky times a s r prime s of r plus r2. Okay, so these are all the terms I have going up to the first nearest neighbor. And actually, the matrix element that I have here, 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 and here are all equal, because I will have to have for this matrix element the S wave here, the S wave here, and the crystal field, but it's exactly the same when the S wave here times the S wave here times the crystal field when I integrate. I mean, with respect, I can transform this part into this part by a reflection. The crystal field remains the same. This part is transformed into this part, and therefore I obtain exactly the same matrix element. So these two are equal. This and this, they are equal. And this are also equal, because again I have to consider the matrix element between this state and the crystal field. And if I rotate by 90 degrees, I transform the crystal field into itself, and I transform this part into this part, so the integration are exactly the same. That is, this integration and this integration give the same metric element. So this is also equal to this and to this. And the same, of course, for R2 and R minus R2. I have S wave to integrate. If I take the reflection with respect to this mirror plane, I transform this product into this product, and the crystal field is also transformed into itself. So the integration gives the same. So they are, all four terms are identical, give the same value, which I will call T. Or let's say minus t, because I know it's going to be negative. For the same argument, the crystal field is attractive. The potential produced by the atoms neighbors of the atom at the origin, they will produce an attractive potential, and therefore this matrix element will all give something negative. So in the end, my epsilon sk here will be equal to the atomic energy plus the shift, which is negative, minus 2t times, if I sum these two terms, I get 2 cosine. So minus 2t cosine of kxa plus, for these two terms, I obtain minus t times 2 times the cosine of ky a. Okay, so this is what I'm getting for the square lattice with one s orbital, for the 1s orbitals. So in this case, it's also of the cosine type, but for both the the kx and ky direction. What will be the width of this band?
It
Yeah.
goes from minus 40 to 40, so it's 80.
Yeah. At the origin, I will have, well, depend. For this part, I will have a 2. And if I consider pi over a for both kx and ky, I will have minus 2. So it will give me a 4 times the 2 here, 8. Excuse
But
me?
I thought that they are in totally different orthogonal directions, so you don't just add them like you were just proposing one on top of the other.
It's a vector k, so it's a 2-dimension.
Yes.
I mean, you have an energy that depends on kx and ky, with kx and ky that can be anything in the Brillouin zone.
Yes, but I thought that if you talk of kx and ky, these ones are totally in orthogonal direction. You just suppose them like they are in one direction.
But mathematically, this is the energy as a function of k. So this is the result. If you take k equal to 0, 0, you obtain here 2. And if you take k equal pi over a, it's you obtain minus 2. So mathematically, it's a function of 2 variables, so you need to. Yeah. Okay? Okay, so now let's look at the case of a 2-dimensional lattice, square lattice, but this time we consider p state in 2 dimensions. So we have, let's say we consider 2p orbital, the px and py.
Yes. Well, those integrals will have just values of units of energy, right? Like
Yes.
And then, so we can compare it with experiments that measure somehow the interaction.
Yes. Yes. Yeah. No, it's in the potential is we have it in as an energy potential, and we normalize our Bloch state as I mentioned initially, that is as 1 when integrated over the unit cell. So yes, it is a true band structure. It's a different method, but it's for calculating the same kind of things than with the plane wave approach. It's just a different way to calculate the band structure in a different limit. That is, in the present case, we are looking at states, electronic states, which are inhomogeneous in space, and their probability density. In the plane wave limit, we look at delocalized states that have a rather homogeneous kind of distribution, like in metal. And in the case of the tight binding approach, we look at different type of states where the probability has a kink on the atoms. I mean, has a high density near the atoms that comes from atomic type of orbitals. So it's a different, for different systems. that one works well with respect to the other. Okay, so now let's continue with the two-dimensional system, still the square lattice, but we consider the 2p orbitals. And the one that should be considered together are the px and py if we consider the two-dimensional space as xy space. So square lattice. So I'm doing again my square lattice. XY. So these are the positions of my atoms. And I'm considering p states, so for the atom at the origin, the px state that will have a positive lobe and a negative lobe, and also the py state, I'm drawing it in dashed line here. So that would be the py state. So px and py. So I will label my states as so the px that is centered at the position Ri, lattice site Ri. I will call it the state I alpha, where alpha is x and y. So this is my notation. The p alpha centered on the site I will just call it I alpha. Now my tight binding matrix will be a 2 by 2 matrix that will involve the px and the py orbitals for the px and py tight binding orbitals. So my metric for the Hawking terms, the T, P alpha, P, let's see, Px, P alpha of K will be, and I consider here the off-diagonal, well, okay, the terms that are for the first nearest neighbors. So this is going to give me the matrix element for the atomic state at the site 0 and the px orbital, v prime 0 alpha. So my Hawking term between the orbital px and p alpha will have as first term the shift here that will be minus delta v0 delta x alpha. Plus so well, maybe I should draw the orbitals. Allora. So, okay. So these are the orbitals. Okay, let me label the site first. This would be the site 0. This is my origin. This is going to be the site 1. This is going to be the site 2, 3, and 4. Okay, these are the I. Now, the orbitals that I have on this site are again px orbitals. So, I'm doing it for all first nearest neighbors. These are the x orbitals, and I have to consider also the y orbitals. So I do the y1 in green, plus minus, plus minus, plus minus, and plus minus. So these are the px and py orbitals of my neighbors. Allora, allora, the matrix element of the diagonal I'm getting just this is okay. So for the nearest neighbors, no, it is okay. So if I have px, I will have a contribution from this term in the diagonal. Then, if I have the off diagonal, the other terms for the first nearest neighbors, on the site I will have something, on the atom 1, I will have kxa times the matrix element between the atoms at the origin, I mean the wave function at the origin, px, the crystal field, and the one, the atomic orbital on the site 1 for the orbital alpha. So I'm just summing over the lattice vectors. So, this is the contribution for the r equal to 0, and these are for the first nearest neighbors. So, then I will have exponential minus I kxa. So this is for this atom, the atom 3. And this gives me the matrix element 3 prime 3 alpha plus, if I sum over the atom 2 and 4, I will have then the neighbors 2 and 4, I will have exponential I ky a times 0x b prime to alpha plus it's I minus I ky a 0 x b prime for alpha. Okay, so this is just the sum over the lattice vectors for the r equal to 0 on the first nearest neighbor. In general, if I consider the atomic orbital px and the as other orbital, tight binding orbital, the orbital p alpha, where alpha can be either x or y. Okay, so far? So this is in general, and now I'm going to look first at the case alpha equal to x. So here I want to evaluate the matrix element for alpha equal to x. So the first term will give a contribution, it will be minus delta v, and the second term, here I have to evaluate the matrix element between the p orbital, px orbital at the origin, and the px orbital on the atom 1. And this is multiplied by the crystal field and integrated. So this matrix element 0x, b prime 1x, I can, it's going to be finite. I will call it T p sigma. And I know that it's going to be positive because here I will have a negative crystal field potential, and I will have an integration over an orbital positive that will multiply an orbital which is negative in the region where they have a significant overlap. So overall, I will have something negative from this product times the negative potential. It's going to give me something positive. So I can expect some value here, which I call Tp sigma, which I expect to be positive with Coulomb type of potential that is the type of potential that I drew before, that is negative in this region. So this is what I expect for this matrix element, and I call sigma what are bonds that point towards each other. Now this other matrix element that I have here, yes?
Please repeat how you are getting the matrix element of 0x and 1x and not telling them to get a negative.
It's this p-type function times this p-type function in red that I have to consider times the crystal field. Now the crystal field is negative, it's an attractive potential in this region. And here I have the product of a wave function which in this region is positive times a wave function which in the same region is negative, so the product will be negative. And then I integrate these negative things times a crystal field that is negative, so it has to give something positive.
I need the clarification on how this one is negative.
This is the definition. I have to have the p states that are all the same. In the type binding approach, the wave function that the linear combination on each side have to be the same function translated on the other side. So I cannot change the phase. I need to take the same one. It's a convention. And then I have this exponential ik capital R for the phase of the next side. This is the way I have written the wave function, type binding wave function from the beginning. So it's with the convention that the P that I use on each side for the phi atomic alpha or whatever, they have to be the same. I'm just meaning my atomic state phi s of R and phi s of R minus capital R, I mean on another side, these have to be the same state. I cannot change the phase there. The convention is that I should use the same, and it's just the same translated on another side.
I understood that, but you were saying that okay, let us consider that one in the origin. At the origin. Yes, you are telling us that this side it is positive.
I mean, the p state is this way. I mean, the p state is a not function by induction. It's like, yeah, okay. Yeah, okay. I'm assuming the atomic orbital have been seen in previous courses. So the p states are states that are odd with respect to the inversion symmetry operation. And they transform like the vector x, y, and z. They have the same symmetric properties. Okay, so now, okay, I just want to finish this and give you so these two matrix elements are the same, have the same value. What I'm saying here is that if I consider the metric element between these states times the crystal potential is the same as the matrix element between this state and the crystal field. And the reason is because I have a mirror reflection here that transforms this state and this state into minus this state and minus this state. And therefore, the product will have the same sign, it will be the same, and have the same magnitude in this region and the reflected region. And the crystal field transforms into itself by this mirror application. So this guarantees that this matrix element with the crystal field and this matrix element with the crystal field will be the same. Because I can transform the orbital into minus times itself. I mean, with the mirror reflection, this orbital is transformed into minus this one. And this orbital is transformed into minus itself. So in the end, the product I get here with the crystal field integrated will be the same as the product I get here with the crystal field integrated. Okay? So these two things will be the same.
Excuse me.
Yes?
What about the TP root?
Oh, so I meant this is the same. So Sorry, my mistake. So this is for this element here, and then the other elements. So this is for alpha equal to x. Now for the red things. Because I want to keep this drawing. So I'll continue in here. I keep the alpha equal to x, and I still need to evaluate these elements, b prime to x, and this I will call t to tp pi. And this, I know that it's going to be negative with a potential that is of the Coulomb type. So this element is the px state here times the px state on the side 2, so this one. I call this element pi because the orbitals are parallel. In this case, I had two p orbitals that point towards each other, and here I have sort of two p orbitals that are parallel, and the interaction is going to go through this channel, but it's weaker. This is much stronger when they point towards each other than when they are parallel to each other. There is still some interaction because here they have the same sign, for instance, so there will be some overlap, but if one integrates, but it's going to be weaker than here. So for sure it's going to be another magnitude. I expect it actually weaker, and I expect it to be negative because in this case I have this times this, which is positive, this times this, which is also positive because they both are negative. So the product is going to be positive, and my crystal field is negative. So I expect in this case something negative, smaller and negative.
Excuse me. In the X line, the plus and the plus and plus were separated, shielded by a minus in between. So we just took the interaction between plus and minus.
Sorry. You mean if I consider these
Yes.
two? Well, I mean, it's a product in our space.
Yes, ma'am.
So
we just
here
took the
it's going to be
interaction part.
something large, but the product of this one, times this one is going to be something very small because this will have a very, very small tail in this region. So this will not matter much.
But in this case, the diagonal part doesn't seem to be that lesser than the like a straight line, plus and plus.
You mean here and here?
Yes, ma'am.
But they are far apart.
So since we are
Here they
considering
point towards each other. You can expect an exponential of one that overlaps with the exponential of the other one significantly here. Here, this distance is, it's much
yes, ma'am.
larger.
So the overall coefficient is weak, but since we are considering it, like we are not taking
it's
it
not
as zero,
negligible,
so
and it's
shouldn't it
considered.
be like a combination of odd and even functions rather than just odd? Because here, since we are considering the interaction anyway, and the distance between the plus positive part of the lower
You
thing and
mean this and this?
yes, ma'am. The cross interaction, like just looking at the figure, it seemed possible Because
it's
not
in the
they aren't that
sense,
far.
on this side, if you ignore this side of the space, on this side you have only positive things, so their product has to be positive. I mean, on the right side of the plane here, you have only positive things, so their product can be only positive. It's a product of the two wave functions in space. So if I'm here, I mean, it can be only, this part can be only positive and this part can be only positive.
Okay, yes. There is like only one action left, yes.
Yeah, if I look at the mirror plane, I mean the plane here, all what comes from these two states is positive, so the product can be only positive. Okay, so this is called this way, and then this metric element is actually the same. No? So I'm saying that this times the crystal field integrated will be the same than this times the crystal field integrated, and again I think it's rather clear from the picture, but the reason is that if I put the mirror plane here, I'm transforming this state into itself and this state into this one. So the integration of this times the crystal field is the same from this times the crystal field, because of course the crystal field with respect to this mirror plane transforms into itself. So one can show that this way that this integral is equal to this integral, and one has this. Okay, basically I wanted to finish. Now if I consider the y direction, the y orbital, that is alpha equal to 1. In that case, what I will have is just zeros for everything. The reason is, so if I have a matrix element between the x orbital at the origin times the y orbital on this side, if I integrate and I have the crystal field, it will be zero. The reason is that with respect to this mirror plane, this wave function is even, it transforms into itself. With respect to the same mirror plane, this function transforms into minus itself, and the crystal field transforms into itself. So one has the product of an odd function times two even function, and therefore the integration has to be zero, because one integrates something that is overall odd. That has transformed into minus itself by the mirror plane. So basically, if you integrate on one side, you can, and you integrate on the other side, they cancel each other. So this matrix element is zero, and the same holds for this matrix element of this wave function times this wave function times the crystal field. Because the crystal field has always, the symmetry is always even with respect to this kind of symmetry operator in your plane. Okay? And similarly, one has that 0x v prime 2y is equal to 0 and 0x v prime 4y is equal to 0. So in this case, I'm saying that the x state px times the y state to y state here, the integration is 0. And the reason is that this state here, Px, is odd with respect to this mirror plane. It transforms into minus itself. Instead, this function here in green, which is the 2y, it transforms into itself through the same mirror plane. So again, one has an odd function that multiplies an even function, and the crystal field is also even with respect to this symmetry operation. So basically, one integrates an overall odd function, and therefore the integration is 0. And the same is valid for this one. So all these matrix elements are actually 0, and in the end, what one gets for the matrix is that the Px element is just minus delta V0 plus 2T P sigma times cosine of Kxa plus 2T P times the cosine of Kya. So this is for the XX metric hopping term in the matrix, and the other one is 0. So basically, the matrix is diagonal. Okay, so I will stop here. I just wanted to finish the... it's okay? You have questions?
Should it be negative for the P pi?
Okay, this, yes, except I arbitrarily said that this time that this is negative, so I should put an absolute value, and the, yeah, it could be, I put the absolute value on the minus. Okay. Okay, so that's it for the first part of the type binding, and it will be an example on the first day of type binding applied to some real system.